non-annular derived link homology. So today and a week from now. So please go ahead, Paul.
Yeah, thank you very much for the opportunity to give two talks here. The title is Derived Annular Khovanov-Rozansky invariants in two parts. This is the title, or it's similar to a title of a paper with Eugene Gorski and Matt Hogenkamp from February this year. So what I'm going to talk about today and also next week is based on joint work with them and also on joint work with David Rose and A Hecke. So this will be about annular link homologies. And there are several motivations for studying annular link homologies in the first place. So maybe the first one is that typically link homologies are invariants of, defined as invariants of links in R3, or the 3-ball or the 3-sphere. And annular link homologies are somehow the first extension to an ambient 3-manifold beyond these initial cases. Another reason is that interesting algebraic structures show up when we extend link homologies to annular links. And maybe a third reason for studying annular link homologies is that certain link homologies actually behave better as invariants of annular links rather than links in usual 3-dimensional space. So the structure of this series of two talks will be as follows. So today I'll start at the very beginning. I'm going to talk about annular link homologies a la Kefelec, Rose, and Sartori, and also studied by many others. And somehow the goal will be to get to the universal annular Khovanov-Rozansky invariant, which is defined using horizontal trace construction for monoidal categories. And this invariant, and especially its target category, will be a categorification of the ring of symmetric functions over Laurent polynomials in a variable Q. And I will do lots of example computations, and I'll talk a bit about open questions. So that is short to say that, so in short, I would say that today I'm going to talk about things that happened before Eugene, Matt, and I wrote this paper, which motivates the sequence of talks. And so next week, I will then go to a derived annular link invariance based on that paper. And so that will result in a universal Khovanov-Rozansky invariant for braid closures in the solid torus, as opposed to a thickened annulus. And it's going to be defined via a derived version of horizontal trace, and it's a step towards categorified skein theory. So that's somehow the plan. This is a learning seminar, and I've been given these 2 hours, so I will start very gently. I see there are lots of experts in the audience, so I apologize once that this is maybe not directly aimed at you, especially what's going to happen today. Okay, so I'll start with some motivation. So, well, we need a few notions. So the first one is, of course, the braid group on n strands. It's denoted BRN. Let me maybe use a highlighter so you can actually. Highlight what I'm talking about. So the braid group on n strands has a presentation. They're n-1 generators, sigma 1 up to sigma n-1, as well as their inverses. They satisfy the braid relations. If these generators are far apart, they commute. The typical diagrammatic interpretation of these generators is that sigma I corresponds to a positive crossing between the ith and the I plus first strands. Sigma inverse is, of course, the negative crossing between the two strands. And the group operation is given by stacking these braids on top of each other. And the convention here is that if you multiply beta 1 and beta 2 to braids in the braid group, you stack beta 1 on top of beta 2. In the braid group. Next item on the list is the Hecke algebra of type A n-1. So the Hecke algebra corresponding to the symmetric group permutations on n letters. So this is defined here as the group algebra of the braid group on n strands over the ring of Laurent polynomials in variable q, modulo a quadratic relation on these generators. So it's best pictured graphically. So it says there's a linear relation between a crossing, an Artin generator, its inverse, and the identity element. And if we rename the classes of these Artin generators as new generators HI, then, well, they still satisfy the braid relations. So braid relation here, the far apart generators commute, and the quadratic relation can be written like this. So this is now presentation of an algebra of Laurent polynomials in Q. You might have seen a different presentation where what I call Q is called V inverse. So it's just another common normalization. And we can think of this as a finite rank algebraic braid invariant. So the braid group itself is, of course, infinite, but this is a finite rank module of the Laurent polynomials. The third notion that I'll need is the Jones-Ognano traces. So they show that there exists a system of traces, means linear functions which satisfy a trace relation. So trace of A times B is trace of B times A, which take so the linear functions from the Hecke algebra on n strands to a certain ring. So this is rational functions in Q, polynomials in A, and the raw polynomials in A actually, for every n greater or equal to 0. And the system of traces is uniquely determined by the following conditions. First of all, the trace of 1, Hecke algebra on 0 strands is just the ground ring. Trace of this generator of the ground ring is just 1. And if you compute the trace of a braid with an isolated strand next to it, then this can be computed by evaluating the trace of the braid itself times a certain factor, this A minus A inverse or Q minus Q inverse. And so this is when you have this isolated strand. And the next relation says, final relation says, if you have a braid of the form a braid on n strands, and then an additional single crossing with the n plus first strand, then you can compute this in terms of the trace of the braid on n strands, and there's just a monomial rescaling. And a similar relation you get when you have a negative crossing instead of a positive crossing here. Okay, the next item here is the HOMFLYPT link invariant. So you can compute this as follows. So given a link in R3, Alexander's theorem tells us that we can present the link as the closure of a braid, non-canonically, of course. And now that we have this braid, beta, any such braid, we can evaluate it in the Hecke algebra. And then once we are in the Hecke algebra, we can apply the trace and get some element of this ring. Let's call it P infinity of beta hat. And then it turns out that this actually doesn't depend on the braid. It only depends on the underlying link. And I should say that the links that I'm considering are oriented and framed. And this is the HOMFLYPT invariant. And basically what you use to prove that this is actually a link invariant is Markov's theorem, which classifies exactly when two braid closures represent isotopic links. And when they satisfy the two Markov moves, the first one says that conjugate braids represent the same. Conjugate braids represent the same link, of course, and then also stabilized braids represent the same links. But the interesting direction of this theorem is the converse, that whenever two braid closures represent the same link, then you can find a sequence of these two Markov moves, two such Markov moves that relate them. Okay, so this is the HOMFLYPT invariant, but of course there's an annular version of this. And it goes like this. So if you have a braid, instead of closing it in a standard way in R3, you can also close it in a thickening of an annulus. Okay. So I draw it like this. So I write beta hat for the annular closure of the link. And so the annulus is this region between the outer red boundary and the inner green boundary. This braid closure is now oriented. It's following somehow the nautical tradition of having green on starboard and red on port. And if you have troubles discerning the colors, you can use these symbols, which are also standard in the maritime setting. So such an annular braid closures represent certain annular links, which are oriented in a way that they keep green on the right at all times and red on the left. And now this evaluates in the cocenter of the Hecke algebra. So if I take the Hecke algebra and I mod out by commutators, I get what is called the cocenter or the trace of the Hecke algebra. And well, so this is an algebraic invariant of braid conjugacy. So this takes somehow it's the home of invariants, algebraic invariants of braid conjugacy classes. And Derived computed that this cocenter of all Hecke algebras, of all type A Hecke algebras, which is also called the HOMFLYPT skein of the annulus, is isomorphic to the ring of symmetric functions over Laurent polynomials in Q. And more specifically, you know something about the Hecke, the representation theory of the Hecke algebra. You know that Hn has irreducible representations indexed by partitions lambda of n, and the map that takes the trace that takes this isomorphism takes the invariant of an element. It takes an element of the Hecke algebra cocenter to the sum over lambdas of sure functions associated to the partition lambda, weighted by the trace of the Hecke algebra element corresponding to beta, evaluated in the irreducible representation V lambda. This is how this identification works. You can, of course, also find other identifications which are then twisted by automorphisms of the ring of symmetric functions. And then once you have this annular braid invariant, which now takes values in symmetric functions, you can recover the HOMFLYPT invariant by evaluating using a certain algebra homomorphism from symmetric functions to this ring.
Well, I have a question.
Yeah, sure.
The natural half algebra structure on lambda q, natural in terms of in language of via HN, but it was using maybe induction restriction of HN or not.
So the multiplication has a very natural interpretation. It's really just putting braids side by side. So putting braids or braid closures side by side. And the co-multiplication has a more interesting or less natural interpretation.
It has more complicated interpretation. So it does have interpretation, it's just more complicated, or?
Yeah, I guess so. I'm not sure it has a very topological interpretation.
Okay, thank you.
But that's been studied by Derived, for example. Okay, so somehow on the decategorified side, the HOMFLYPT invariant of an annular braid closure is a symmetric function rather than just a polynomial invariant. And see, Nito Kichlu asks whether the slides can be made available, and yes, I'll do that, but I haven't done it yet. So I'm sorry, I didn't manage to share the slides yet, but I will do. Okay, so a few remarks. So at first sight, this function tr which takes annular braid closures to symmetric functions is really an invariant of links in the thickened annulus. So I'm writing A for the annulus, so circle times interval, and then it's thickened again by an interval direction, which is somehow orthogonal to the drawing surface. It's perpendicular to the drawing surface. And if we want to, if we would like to start instead with a positive link in a solid torus, so S1 times a disk, then we first need to identify the solid torus with a thickening of the annulus. So we have to choose an I-bundle structure before we can write the link as the closure of a braid. And the ambiguity that appears here is from the perspective of the solid torus, just a Dane twist, or from the perspective of the braid closure, it's somehow full twist insertion. It's the insertion of some integral power of a full twist. And to illustrate this, let's look at this annular unlink with two components in a solid torus. And here we see a standardly embedded solid torus, like we usually draw it. But if you want to translate this into a braid closure, you have to choose an I-bundle structure. And if we choose the standard equatorial annulus in there and project onto that surface, we would just see two concentric circles, like on the left here. But we could also use a different annulus to project. So for example, we could use the one on the right, and relative to that annulus, we would actually see a negative full twist in these two, between these two concentric circles. And so they differ by insertion of a full twist. So this is actually very natural because the full twist generates the center of the braid group on n strands. And as usual for algebras, you have in this case, the Hecke algebra, you have an action of the center of the Hecke algebra on the cocenter. Center always acts on cocenter. And a topological interpretation of this is the following. So suppose you have a central braid, some power of the full twist in this case, and you have the invariant of an annular link here, an annular braid closure. What you can do is you cut the link somewhere and you insert the central braid. And because it's central, it doesn't really matter where you cut. So this is a well-defined operation. Now, this cocenter of all the Hecke algebras is isomorphic to the ring of symmetric functions over Laurent polynomials. So here's a quick question for you to think about if you're bored. How does the full twist act on symmetric functions if you use the dictionary? So we'll see an instance of that a little bit later on. Okay, and the motivation now is to, or the goal now is to categorify most of the story that I've been telling so far. But before that, I want to introduce some tools that are useful even before categorifying. So we'll have to go through a few more notions. So the first one concerns different bases for the Hecke algebra Hn. So maybe the most natural one, the first one that you would meet is, well, you just look at the classes, the invariants of positive permutation braids. So let's take a permutation W. Let's fix a reduced expression of this permutation in terms of elementary transpositions Si. And then define HW, which actually depends on this. So at first it depends on the reduced expression, but then we'll see that it actually doesn't. So HW underscore is just the product of the classes of the Artin generators indexed by these indices I1 up to I length of the word. And they form a basis, which you can check using the relations, the defining relations. An algebraically maybe more interesting basis is the famous Kashmiristic basis, of course, still indexed by permutations. And we will only need the cached and loose-tick basis elements associated to simple reflections. So for a simple transposition, SI, the corresponding cached and loose-tick element BI, you can actually express in two different ways. In terms of the class of the positive crossing and the identity element, and in terms of the class of the negative crossing between the ith and the ith plus first strand and the identity. And I typically like to illustrate these things. So crossings I like to draw as crossings. The unit element I like to draw as an identity braid. And then this cached and loose-tick basis element associated to simple transposition I like to draw as a thick edge where two strands come together, they merge. They go into a little line of double the thickness, and then they split off again. And already from these two expressions, you can see that this element is actually invariant under the involution of Hn, which just exchanges positive and negative crossings and sends Q to Q inverse. And if you extend this to arbitrary braid word elements, then this sends HW to the inverse of HW inverse. Okay, so this is a very nice basis. If you work with this basis, no, okay, so we won't work with this basis, but we will work with these generators BI. So the HIs were generators, so this triangular equivalent BIs are also a basis, and we can compute what relations they satisfy, and you'll see a perturbation of the braid relation. So instead of the honest braid relations, you have braid relation plus some lower error terms. You still have some kind of far commutativity, and the quadratic relation turns into a positive a quadratic relation with positive coefficients, which is useful. And from these generators BI, we can build another basis, again indexed by permutations, but now we should really pick one reduced expression for each permutation, and we define BW underline as the product of the corresponding BI generators, and let's just call them webs. And let's draw them as webs, so as products of these thick edge generators. And then I've drawn for you the relations that they satisfy. So the first relation is this somehow perturbed braid relation, which now you see in blue here. There's still far commutativity, and there's this quadratic relation which now has positive coefficients. So a question that I find very interesting is since these are elements in the Hecke algebra on n strands, and we can compute the corresponding symmetric function given by this universal trace. So what are these symmetric functions if we evaluate them on the cached and loose-tick basis or on this basis of webs, BW underline? Okay, I won't answer this, but I just want to put it out there. The next tool that we need is Soergel duality. So classical Soergel duality operates with the symmetric group on n strands, and the universal enveloping algebra for GLN, now a different n, capital N. And what you do there is you take the vector representation of GL capital N, you tensor it n times, and now you have commuting actions of the symmetric group and the universal enveloping algebra for GLN on this tensor product. They commute, and they actually generate each other's centralizer. There's a quantized version of this, so pure Soergel duality, where you replace UQGLN by the corresponding quantum group. You replace the vector representation by the analogous vector representation, which is now defined over rational functions in Q. And on the other side, you don't get the symmetric group, but you get the Hecke algebra. And you have the same relationship. These actions commute and generate each other's centralizer. And this is useful because that means, in particular, viewed from the left side of this duality, that you get a surjective map from the Hecke algebra into endomorphisms of that tensor product that are equivariant for the action of UQGLN. And this space of UQGLN equivariant maps is exactly where the Reshetikhin-Turayef braid invariants for the quantum group associated to GLN live. And it actually turns out that if n is large enough, and somehow that's the case that we're interested in, so this HOMFLY invariant is somehow the large n limit of the GLN Reshetikhin-Turayef invariants, and this becomes an isomorphism. So Hn completely encodes the finite dimensional representation theory of polynomial representation theory of UQGLN that we need to study these braid invariants due to Reshetikhin-Turayef. Yeah, so that's Q-Shu-Val duality. There's a more fancy version of a similar tool. It's called Skew-Skew-How duality. Instead of the Hecke algebra, so it's again a double centralizer story. But this time we use two instances of a type A quantum group. So on the right, we still have UQGLN, but on the left, we now have UQGLM. And so we take the vector representation for the thing on the left and the vector representation for the thing on the right and tensor them and then form the exterior algebra, or actually the n-fold exterior power of this tensor product of representations. Now you have the same statement. So two commuting actions generating each other's centralizer. And from the viewpoint of the action on the left, we can look at the weight spaces. So for a dominant integral weight for GLM, which you now denote by a tuple of non-negative integers n1 up to nm, the weight space for this weight in the representation here on the middle is just a tensor product of exterior powers of the vector representation for the UQGLN on the right. And similar as before, we can use this just looking at the left side of this duality to get a surjective map from the quantum group associated to GLM, and more specifically from Lustig's idempotent version of the quantum group for GLM into Hom spaces in the representation category of UQGLN between tensor products of fundamental representations of UQGLN. So this gives us a way of encoding all the UQGLN equivariant maps between fundamental UQGLN representations. So these tensor products of the tensor products of exterior powers of the vector representation, or tensor products of fundamental representations. And this is exactly where the wedge-colored Reshetikhin-Turayef invariants of braids live, where you're allowed to put a fundamental representation of GLN on any component of the braid. And this dictionary has a visualization again. So UQGLM, so if you remember one thing here, is that this UQGLM is a non-unital algebra. Instead of a unit, it has some idempotence, but it still has typical elements EI and FI, where I ranges over the simple roots GLM, and an EI together somehow acting on the idempotent associated to weight n, we can visualize as a certain more complicated web it now has, so you still see lots of uprights, but now they have some thickness, and the thickness at the bottom is given by this GLM weight and underline. And then the E is visualized as a little run in a ladder, moving weight to the left by 1. So this should correspond to a certain UQGLN intertwiner between a tensor product of exterior, so fundamental representations, which are indicated by the labels on the bottom, to the corresponding tensor product of fundamental representations indicated by the labels on the top. And these intertwiners are built from very simple pieces. So if you see in such a graph two edges merging into one, so you have labels A and B and they merge into A plus B, then what you do is you simply wedge vectors in wedge A and wedge B together to get a vector in wedge A plus B. And then there's also a very natural intertwiner going the other direction, which are of course not inverse to each other. And somehow, if you know what happens to somehow to interpret these basic graphs as intertwiners of UQGLN representations, then you also know how to interpret such a big and more complicated web. But that's how this goes. The cool thing about this way of describing the representation, of accessing the representation category of UQGLN is best summarized in a theorem of Countess, Chemnitz, and Morrison. And what they do is they study the kernel of this surjective map from Lustig's idempotent version of the quantum group associated to GLM into this space of intertwiners. And they show that this kernel is actually generated by certain idempotents, namely the idempotents associated to weights where the entries of that GLM weight don't lie inside the range between 0 and n. So if we look up into this dictionary, a weight should correspond to a tensor product of exterior powers. And now for example, if these numbers are negative, then the right-hand side doesn't make sense. And if one of these numbers is greater than n, then the thing on the right-hand side would be 0 that corresponds to it, because you would take an exterior power that is just too large. And so it seems very natural that this kernel is generated by these weights where the entries are not all entries are between 0 and n. And this is indeed the case. And this gives you a presentation of the category of fundamental representations of UQGLN in a diagrammatic way. That means as a pivotal tensor category, and it does so. This presentation is given in a diagrammatic way by generators and relations. The generators are these trivalent vertices, which you can combine in a planar fashion. And then there are certain relations. And some of the relations we've actually already seen in the context of the web basis for the Hecke algebra. And the really cool thing is that this presentation conjecturally works over Laurent polynomials in Q with integer coefficients. And maybe this is the strongest reason for why link homology works so well in type A. Oh, and Ben says he proved it for all n. That's awesome. That's good. So I'll fix that. Okay, so let's do an example how you can extract web relations from the quantum group associated to UQGLM. So let's take m equals to 2. So m equals to 2 is now on the how dual side. So that will say something about webs which have at most 2 upright components. And one relation in UQGL2 is the relation that EF equals FE plus quantum 2. Okay, so it seems very familiar from usual Lie algebra theory. And now the diagrammatic interpretation is like this. So we evaluate this at a weight with entries 2 and 0. So we're looking at webs which have boundary labels 2 and 0 on the bottom. Now on the left-hand side, we first do F. F takes a weight, it takes 1 from the left strand, moves it over to the right strand. Now you're in weight 1, 1. Then you do E again, which moves this thing back and merges it back into a double thickness edge. That's the thing on the left. On the right, we first see FE. So first we would do E, but E wants to move some weight from the right strand to the left strand. So we'd start at 0 and try to move 1 over to the left, but then it would create a negative weight there, -1. That doesn't have a web interpretation. So this entire thing will be 0. And the only thing that remains is this web on the right, which just is the identity on the weight 2, 0. And so we just interpret this as a single thickness 2 strand, and it comes with coefficient q plus q inverse. And now let's compare this to this Hecke algebra relation that we've seen, that bi squared equals q plus q inverse bi. Okay, so if you remember how these bi's look like, there were somehow these dumbbells on double edges, and now I'll draw them like this. So bi squared looks like this. Sorry, I'm a bit hard to write on the screen. So we've seen this relation before. Okay, so now how do we actually compute this symmetric function value trace of a braid in practice? So I would say, and I've actually coded this in the following way. First step, take the class of the braid in the Hecke algebra, and now change basis from the basis given by products of crossings to this bi basis. So in practice, this means replacing crossings by a linear combination of 2 planar pictures. One is this web with a thick edge, and one is the parallel resolution web. And if I want to, I could also say that I'm replacing this crossing by a linear combination of elements in this skew-Hao dual quantum group, Fe minus identity, or minus the identity plus Fe. And I have a minus sign missing on the right. Okay, so for example, for the full twist, what we would do is we would first replace the top crossing by a linear combination, then we would replace the bottom crossing. We get some linear combination of webs, and we can further simplify them, especially this web on the left. You see it has a diagon in the middle. This diagon can be removed at the expense of multiplying by q plus q inverse, and then we do some algebraic cancellation, and we get a linear combination as shown on the right here. Highlight this. No, don't like to highlight. Here we go. Okay, so this is the first step. The second step is annular simplification, and this is a term coined by Keflik and Rose. The idea is to simplify each annular web into a linear combination of concentric circles, and the circles are then allowed to carry labels. So in the case of our favorite Fe web, what we would do in the annulus is we would slide half of that web around the annulus. Then we see a diagon, and then we can remove the diagon at the expense of multiplying by q plus q inverse. What we're left with is a single circle in the annulus, an essential circle in the annulus with label 2. This is an example, but how does this work in general? Well, maybe the cleanest way of saying this is use skew-Hao duality, use this quantum skew-Hao duality, together with the fact that UQGLM has a triangular decomposition, or even stronger, PBW theorem. Mark asked the question.
Yeah, right. So in this picture here, right, you have, in the example you did before, you had 1, 2, 0, and so on. But if you go up a little higher for when you were going between the Hecke, yeah, there. Oops, no, a little lower, a little lower. There. Right, you have FIEI and you have 1 sub 1.
Oh, yes. So I had one underline, and one underline
One
says,
underline.
yeah, one underline. One underline says, means take the weight, all of those entries are 1.
Got it. Now it makes sense.
Okay. Great. So if we just work with the Hecke algebra, that's what we start with. You could also work with a Schur algebroid or some kind of fancier version of the Hecke algebra where you could allow other ways to start with. But if you just work with the Hecke algebra, that's what you start with. Okay, good. So, okay, so we're back. Yeah, so we're back at this question, how to write how to rewrite an annular web as a linear combination of concentric circles. And the idea is whenever you start with a web, so now that translates into some element of a quotient of UQGLM. And this in UQGLM, you can write every element as a linear combination of certain monomials in Fs followed by E's. And diagrammatically, this means you have you expand this linear combination of diagrams where you first see letter webs with E's, so somehow strands moving to the left, preferentially, and then F's. So then after all the E's, after moving left, stuff is allowed to move right again. And if you're not the identity web, then you need to have one E or one F, at least, and one F appearing. And that means that in the middle of this picture, somewhere in the middle of this picture, you'll see a weight, one sub L underline, which is higher than the web that you started with. And since you're in the annulus, you can now slide the top half of this diagram around. And now you're again stuck, you're again in the situation that you have some kind of web, and you would like to value it further, but somehow you're one step closer to the answer because the weight that you're starting with is higher. And if you iterate this procedure, so you now write this EF thing again as an FE thing, and then keep going with this algorithm, it will terminate. And it will terminate exactly in the case where you cannot find, where you cannot expand your web anymore in an interesting way in FEs. That means in the case where your resulting web is actually an identity web, it's just parallel strands going up. And in the annulus, this means it represents some concentric circles. Once you're there, you're at step 3, you can now read off the trace of this braid or of this Hecke algebra element simply via the following dictionary. If you see a web which just has concentric circles with labels C1 up to CK, then you translate this into the symmetric function, which is given as the product of elementary symmetric functions ECI up to ECK. So a single circle corresponds to an elementary symmetric function, and parallel concentric parallel circles correspond to the product of those. Let's do an example real quick. If you have the full twist, then we've already simplified this Hecke algebra element into a linear combination of braids. Then we've already simplified each of these EF webs into Q plus Q inverse times the 2-labeled edge. And then there's an algebraic cancellation. And the third step, we just read off the symmetric function. So each of these 2-labeled edges becomes an E2, and second elementary symmetric function. And this thing with 2 parallel ones becomes E1 squared. And if you expand this in terms of Schur functions, maybe the favorite basis of the ring of symmetric functions, you see Q squared times the 2 boxes in the column Schur function plus Q to the minus 2 times 2 boxes in a row Schur function. And now compare this with the trace of just the identity braid. This somehow has the same Schur functions, but with different powers of Q. Here are a few more examples of such traces. So if you take a positive Coxeter braid, then the corresponding symmetric function is an alternating sum of hook Schurs in this large region, and you can interpret it as statistically substituted complete symmetric function. And there's a more general story where you can express the trace of an arbitrary braid lift of this Coxeter element, so with arbitrary signs of the crossing as some statistically transformed Rubin-Schur function, depending on the sequence of signs of these crossings. Something that Eugene and I proved in the paper from last year was that if you have a web or a Kashmiristic basis element associated to some permutation in Sn, then these symmetric functions that you get are Schur positive. And there's a conjecture of Keflik and Rose in the case of webs, and also for Kashmiristic basis elements, that these traces are actually positive in the basis given by products of elementary symmetric functions. This is much stronger. I'm not going to say much more about this conjecture, but it's a seriously interesting one. Okay, so we're getting close to the end, but I still want to make a little bit more headway towards categorification. Most of this will actually have to appear next time, but let's get started. So the main tool here are Soergel bimodules. So here, let's fix this number n, the number of strands greater or equal to 0. And let's consider the polynomial ring on n variables, and we consider this as a graded ring, or as a graded algebra with complex numbers by putting the x's in degree 2. I'll always put a little cheat sheet, some pictures that you should have in mind for these algebraic gadgets on the right. So you should think of this as somehow the identity braid on n strands. And inside this ring R, we can look at the sub-algebra of polynomials that are invariant under swapping xi and xi plus 1. And more explicitly, this is just a ring of polynomials in the x's, except that xi and xi plus 1 have to appear symmetrically. So somehow the polynomial generators here are the first two elementary symmetric polynomials in xi and xi plus 1. And then you form this thing bi by tensoring two copies of R over invariants under swapping xi and xi plus 1, and then shifting the grading down by 1. So this is called a Bott-Samuelson bimodule. And you should think that it corresponds to this picture where we have not quite an identity braid, but we have the ith and the I plus first strand merging into the edge of thickness 2, and then splitting off again. And then the category of Soergel bimodules of type AN-1 is defined as the full subcategory of graded RR bimodules containing R itself, the identity bimodule, and these BIs for all I, and it's closed under tensor product over R, so that's the way you compose bimodules, taking direct sums, taking direct summands, and performing grading shifts. So this gives you a graded linear monoidal category. It's linear but not abelian. And it's designed in a way that its growth-in-Lie ring is isomorphic to the Hecke algebra on n strands. Okay, I'll maybe wrap up in 2 minutes or so. Let me just say a little bit about the singular Soergel bimodules. So this is what corresponds to the more general webs that we've seen before. So singular Soergel bimodules are defined as the full sub-2 category of graded bimodules now over several different rings. And they're built from, well, you take the ring R and you look at polynomials in there which are symmetric for this parabolic subgroup of Sn. So you have permutations of the first n1 strands and so on. It's permutations, yeah. So this parabolic subgroup of Sn, and then you can induce up to this other parabolic subgroup. In any case, I mean, if you look at this, this thing itself is a module on the left over this ring. It's a, let me just highlight here. So I'm talking about this thing. It's a module over the thing on the left here, and it's a module on the right over the other thing. And you should think about it has a certain width where some strand of thickness ni plus ni plus 1 splits into two strands of thickness ni and ni plus 1, and the other way around. And then you build a two category from that by allowing stacking of these things, which means tensor product over the corresponding intermediate rings, taking direct sums, taking direct summands, and performing grading shifts. So this gives a graded C-linear two category, again not abelian. Okay, and I think I'm out of time for now. I'll continue next time, but for now, yeah, now I'll stop. I'm happy to answer questions.
Thank you. Let's thank Paul.
So is there a way to go from this story of taking traces of braid closures to somehow annular link homology, or are these very different stories?
Yeah, so that will appear very soon.
Okay.
Yes, so there's a completely, that's the story that I want to tell. So if you have a categorical invariant of braids, and we'll get there very soon, maybe by computing Rouquier complexes of Soergel bimodules associated to braids, there's a completely formal construction which somehow takes an annular closure, and it's called horizontal trace. And yeah, so I'll talk about this next time. And this is somehow the most universal thing you can do to impose a trace relation on a monoidal category.
But there is one difference. It seems that like when you take the annular closure here, you're moving all the strands around the annulus. So the only annular link homology you're going to get are going to be the ones which involve like I guess an n-dimensional irreducible representation of SL2, right? You're only gonna, because you need to take n tensor products. Whereas you could have moved the dot somewhere else, and you could have moved the annulus somewhere else, so embedded this in the annulus in a different way where you don't see such large irreducible representations of SL2, right?
So at the moment, there's not just SL2 involved. So at the moment, this is completely agnostic about the rank of the Lie algebra. There indeed, so there will be a way of specializing to SL2, but for now, the only parameter is somehow the total thickness of the braid. And now this is a weighted thickness. So you're allowed to put wedge colors on the braid strands, and then you have to work with these singular Soergel bimodules.
Can I ask? Was that like this works for annular braid closures, but it doesn't in principle define any invariant for annular links which are not braid closures?
Correct.
Ah, thank you. Yeah.
Quick question, if you don't mind. Paul, can you hear me?
Sure, yes.
Yeah, thank you very much. Actually, it's a very helpful talk. It sort of gives me perspective as an outsider. I have a question that's more philosophical. The description that I have seen and that you've outlined, and presumably in your next talk, it'll be categorified, is that everything seems to descend through the Hecke algebra or some categorification in terms of Soergel bimodules. Is there a reason why you want to factor through the Hecke algebra and not the group algebra, the braid group? In other words, my question is there structure you can impose on these constructions that will force you not to factor through the Hecke algebra, but work with the entire group algebra, the braid group?
Good question. I don't know. Ben, I think Ben has an opinion. Ben was nodding.
I mean, it's something that you can think about when you're thinking about categorical actions of quantum groups, for instance. You've got this sort of braiding Ricard complex, which is some long thing, and how it acts on the zero weight space is this long sequence, which is like the identity in homological degree 0, and then EF, and then E divided 2, F divided 2, E divided 3. So it's this long complex, arbitrarily long.
Right.
But when you're acting on the representation that it acts on in Schur-Weil duality, E divided 2, F divided 2 is 0. So it's actually just a two-term complex. And EIFI is this BS thing that he's been talking about. So you end up with this two-term complex, which is how the categorical quantum group braid group action actually acts on the zero weight space. And this is the reason it factors through the Hecke algebra. The fact that it's a two-term complex is like the zeroing of some next thing, which is a quadratic relation.
So maybe I should give some perspective of where I'm coming from. The reason I ask is because there is this, recent development of throwing in operations on these. Well, once you categorify, you sort of have these potentially extra homology operations, if you will, that act on this whole construction. And my understanding is that's a good test place to see if those operations will then eventually give you an object that does factor through the Hecke algebra, or that's going to break that kind of symmetry. And if it does, then the question, of course, naturally is that maybe, there's something going on there that's somehow larger. And this is a naive question. And I'm just trying to give perspective on what kind of, what motivates the question that I just asked.
Maybe I want just to comment that, first of all, the entire group algebra of braid group is infinite dimensional. So it's harder to manipulate. And usually we look at finite dimensional quotients that go through representations of quantum groups. I can take any representation, take its K power, and you have a braid group acting on it. But then it's combinatorially it's much harder to study representations of the braid group coming from representations other than the fundamental representation of quantum SLM. It's just combinatorially harder. And then we also don't know how to categorify them efficiently because there is no analog of the so-called MOY calculus, Murakami-Atsuki-Yamada calculus, which has really nice positivity and integrality properties. And that's lacking for other representations of both GLN and other quantum groups. So it's the case where you have a sufficiently easy combinatorial structure before clarification to lift it efficiently to categorify it. So it's just much harder once you change your representation from the action of the braid group on V tensor K, where V is the fundamental representation of quantum SLM, to pretty much any other representation of any quantum group.
Yeah, so that certainly makes a lot of sense. Yeah, that's helpful. Thank you.
Paul.
Yeah.
Is there a by the way, is there a better way to ask questions other than just to chime in? Should I be raising my hand, or not really sure if anyway. So you had a conjecture with you and Eugene above, but I didn't get a good look at it. I was wondering if you said you weren't going to talk about it very much, but I was curious what it.
This E-positivity conjecture?
Yeah.
Yeah.
So the conjecture is that for every web, this symmetric function is E positive?
Yeah, exactly.
Okay.
Exactly, and you can strengthen it, and you can say every Kashmiristic basis. So this concerns webs with boundary points labeled by ones, and you can strengthen the conjecture that actually the Kashmiristic basis elements, the traces of the Kashmiristic basis elements are E positive.
I see. So categorified, this is saying that the corresponding object in the DG trace or whatever is supported in one cohomological degree.
So that would be short positivity, which we proved, I guess. I mean, it depends how far you decompose. If you're only decomposing to E's, then yes, that's what this conjecture would.
Okay.
Yeah. But if you decompose into Schur's, then we already know that it's.
Yeah.
Yeah, but. Yeah.
I actually also had a question for Neetu, based on just a secondary question. You mentioned these cohomology operations for link homology. Is there any? Do these make sense just for closed links though? I wonder what it means to factor through the Hecke algebra anyway, I was curious how one would ask that question unless you could make some sense of the cohomology operations for braids.
So the only, okay, so as far as I know, the cohomology operations that I'm aware of, I mean, they're the two types, right? There's the Lipschitz-Sarkar type Steenrod operations, and then they're the ones that Mikhail and Lev have created, this sort of the Witt algebra operations. So there may be others, I'm just not aware of them. So, and both of them, from my understanding, well, at least the ones that Mikhail has constructed, my understanding is that they don't respect the Hecke structure. In other words, you don't get the idempotent decomposition in certain bimodules to be respected, to continue to be respected under those operations.
Well, it depends what you mean by that, but.
So I don't, I don't know this well enough to be able to make statements beyond the generality I just did. So what I simply mean is that, if you have the idempotent decompositions, you'd expect in the Soergel bimodules, and then you enrich them with these Witt algebra representations, then the idempotent decomposition no longer holds. And so that just gives me the sense that maybe if there's something bigger going on that comes endowed with all of these representations, then perhaps, one has to investigate what's going on here. Is there some bigger picture? That's sort of like the naive way of seeing. And so from that standpoint, I guess you're working with braid closures, right? I mean, the construction I know of these actions is not general for linked diagrams. It's sort of specific out of braid closures. So maybe it's very specialized. It's a long answer to the question that you just asked.
I'll add a little bit, which is that it's certainly true that the decomposition of say a Bott-Samuelson bimodule or a tensor product of Soergel bimodules into indecomposables doesn't work with respect to the Witt operations, but there are lots of parts, some of the decompositions are at least filtered with respect to the Witt operations. So you still get some sort of categorification in the Hecke algebra with a different basis. It's not the Cauchy-Lewis-2 basis anymore.
Sounds interesting.
There are these three types of homological operations. There's Lipschitz-Sarkar on SL2 homology, and that doesn't require braid presentation. And there are U operations that you introduced last year on various versions of strictly graded homology, HOMFLYPT homology, and that requires a braid presentation. Then there's my old work with Lev on the Witt algebra action. And so probably the last two are somehow related, but I mean, I don't know any results. But I just want to point that at least 2 out of 3 do require braid presentation of the link, and which is also true for many link homologies. I think it's a major problem to get rid of the braid presentation requirement to define the separations, to define various homology fields. It's kind of a big, probably related problem to pass to more intrinsic definition using, say, for instance, braid diagrams that are, using planar diagrams that are themselves not fully intrinsic, but intrinsic enough, kind of somehow more intrinsic than braids. Because there's less symmetry breaking in a planar diagram presentation than in a braid presentation in this sense. Okay, I will ask a completely unrelated question. I want to ask Eugene and Lev whether how can we find out the Zoom info for the mini course by Lev? Let me repost the link in the chat. Mini course next Monday. So how does one sign up? Does one contact Andrei or Lev, or is there some other way?
There is no need for signing up. As far as I understand, there is a website for the seminar, which has a link to Zoom talks. It's a small link. I think it's hidden somewhere on top of the page. So it's a tiny link, but it's explicitly there.
But right now there are no links on that site. Right now there are no links.
Sorry, let me try it.
I think if you hover on one of the subtitles, there is actually a little link on the right that shows up.
on the subtitles. Is that upper left or upper right?
In the middle of the screen, I think, and then you'll see that on the right, a little link icon shows up. You just hover over his name or the title.
That looks like a link to the same website that you're just at, though. I copy paste.
I guess there are 2 links. I see 2 links. Oh, I see. Copy.
No, I think if you go to this main seminar, like informal math physics seminar, there is a link on top of it. So seminar meets in cyber.